In the realm of physics, force is the invisible hand that choreographs the dance of objects through space and time. It's the unseen influence that can change how something moves or even alter its shape. But how do we experience this fundamental concept in our everyday lives? Let's delve into the push and pull of forces, exploring their magnitude and direction. Imagine you're behind a stalled car, hands pressed against the trunk, muscles tensed. As you shove forward, you're not just moving a vehicle, you're exerting a push force. This force is a vector with both strength and direction, propelling the car away from you. Similarly, when your finger descends on a button, you're applying a push force, activating a device with a simple gesture. And think of a baseball pitcher, their arms swinging forward, pushing the ball into a soaring arc across the field. Each of these actions embodies the essence of a push force in physics. Now, envision the opposite motion. You grasp a door handle and pull it towards you, exerting a pull force that draws the door open. Or consider the act of tugging a rope, each pull bringing the tied object inching closer to you. Even the unseen power of a magnet, drawing metal objects into its invisible embrace, is a classic example of a pull force at work. These scenarios illustrate the pull force, characterized by attraction and movement towards the point of origin. Both push and pull forces are the linchpins of motion and interaction. They are the silent orchestrators of everything from the microscopic dance of particles to the majestic waltz of celestial bodies. Understanding these forces as either a push or a pull is more than academic. It's a window into the mechanics of the universe, offering insight into the very nature of how objects respond and behave under the influence of applied forces. The power to move, from rest to motion. The world is in constant motion, but how does it all begin? Picture a dormant object, lifeless until a force breathes movement into it. This is the essence of Newton's first law of motion. An object at rest will not move unless compelled by an external force. Imagine the effort needed to push a stationary car into motion. That's force overcoming inertia, sparking kinetic energy, and setting the wheels in motion. Halting the momentum, motion to rest. But what about bringing a moving object to a standstill? It's the reverse scenario, where force acts as a barrier to motion. When brakes clamp down on a bicycle's spinning wheels, they exert a force in the opposite direction, bleeding away the kinetic energy until the bike ceases to move. It's a dance of dynamics, where force and motion play out their eternal tug-of-war, speed variations, acceleration and deceleration. Force is not just about start and stop, it's also the maestro of speed. Newton's second law tells us that an object's acceleration is a duet performed by the magnitude of force and the object's mass. A stronger force quickens the pace, increasing speed, while a force in the opposite direction is like a gentle hand on the shoulder, easing the object to a slower tempo. A new path, changing direction. Now envision a force that doesn't push or pull along the line of motion, but strikes from the side. This perpendicular force is the sculptor of new paths, bending motion without altering speed. It's the centripetal force that keeps a ball spinning in a circle, tethered by a string, a celestial dance replicated in the palm of your hand. Reshaping reality, the impact on form beyond motion, force is also a shaper of matter. It can warp the very form of an object as seen when a spring stretches or a rubber ball compresses. Hooke's law gives us insight into the elasticity of materials, a knowledge that engineers harness to create structures that can endure and rebound from these transformations. In the grand tapestry of classical mechanics, force is the thread that weaves through every change, from the stillness of rest to the dynamism of motion, from the rush of speed to the elegance of direction, and into the heart of matter itself. Understanding these principles is not just academic. It's the key to mastering the physical world. In the realm of physics, forces dictate the motion of objects around us. But not all forces are created equal. Let's delve into the fascinating dynamics of balanced and unbalanced forces and their impact on the world as we know it. Picture a serene scene, a book lying motionless on a table. It's a perfect example of balanced forces at play. The book is subject to the relentless pull of gravity, dragging it downwards, while the table exerts an equal and opposite force upwards. These forces cancel each other out, resulting in a net force of 0. Consequently, the book maintains its peaceful state, neither moving nor accelerating. It's a delicate dance of forces, each perfectly countering the other, creating equilibrium. Now let's shift gears and imagine a car cruising down the road. The engine roars, exerting a hefty 500 newtons, propelling the car forward. However, friction and air resistance are in opposition, mustering a combined force of only 300 newtons. The result? A net force of 200 newtons thrusting the car to the right. This unbalanced force disrupts the status quo, causing the car to accelerate in the direction of the net force. It's a clear demonstration of how unbalanced forces can spur change, setting objects in motion or altering their trajectory. Understanding the tug-of-war between balanced and unbalanced forces is crucial to grasping Newton's laws of motion. It's these principles that explain the behavior of objects under external influences. Whether at rest under a balanced force or in motion due to an unbalanced one, the forces at play are the invisible hands that shape the movement of everything in our universe.